Hello everyone, I'm Deokhwa, and today I will present our paper titled Overlap Bootstrapping for FHEW TFHE and its application to SHA3. And this is a joint work with Choi, Lee, Kim, and myself. Here is the outline of my presentation. I will begin preliminaries where I will review the background and notations used throughout this work. Then I will introduce our core idea, the flexible scaling factor, which plays a key role in reducing noise during homomorphic computations. After that, I will explain the concept of overlap bootstrapping, a method we propose to improve efficiency of homomorphic computations. Finally, I will show how our method can be applied to evaluate cache-up, the SHA3 hash function. And this is preliminaries. And Deokhwa and Xiu first introduced FHEW-like homomorphic encryption with a brilliant homomorphic decryption circuit in their system, called blind rotation. This is one of the best known bit-level homomorphic encryption schemes, and it has a smaller bootstrapping complexity and key size compared to other encryption schemes. And bootstrapping is one of the most expensive operations in homomorphic encryption. Due to this property, the FHEW-like scheme is a useful tool in constrained environments such as small devices. It is also used in smart contracts within the fully homomorphic Ethereum virtual machine called FHEW. And secure hash algorithm is an important part of smart contracts, often used for verifying data and ensuring integrity. And recently, JAMA introduced a challenge to build SHA-256 using fully homomorphic encryption, and which shows the growing interest in applying fully homomorphic encryption to real-world cryptographic functions. In this work, we focus on evaluating cache-up. These are the main contributions of our work. First, we implement SHA3, also known as the cache algorithm, using FHEW-like schemes. Next, we improve its efficiency by applying method, reducing the runtime by approximately 44%. Also, our method does not require additional key generation or extra evaluations, which helps keep the client's workload minimal. And moreover, our approach is not limited to this specific application. It can be applied to any computation that involves consecutive XOR gates, making it broadly useful in various fully homomorphic encryption applications. Now we introduce encryption and decryption that used in FHEW-like schemes. Encryption is simply performed by adding a scaled message to the inner products of A and S, along with a small amount of noise. Here A represents random numbers, while S is the secret key. The secret key S is sampled from a binary, ternary, or Gaussian distribution. A message M is a single bit, and delta is the scaling factor, commonly set to Q/4. And it is also provides some resistance to noise in the message. And decryption is straightforward. By subtracting the inner product from the ciphertext, we retrieve the message with only a small amount of additional noise. And I will introduce the bootstrapping process used in FHEW-like schemes. And this figure illustrates the bootstrapping procedure in FHEW-like systems. First, we compute two ciphertexts using the ODAT operation, followed by ACC initialization. Next, we perform the homomorphic decryption circuit known as blind rotation and extract the constant term from the output. Finally, we switch the modulus and keys to enable further operations. And this step is necessary because FHW uses two cryptographic problems, LWE and RLWE. During bootstrapping, the ciphertext is temporarily converted into the RLWE format. To return it back to the RLWE format, and which is used for regular computation, we need to switch both the modulus and the secret key accordingly. And the ODOT operation has distinct definitions depending on the gate operation and being executed. One important point to note is that XOR and XOR gate operation introduces additional noise due to their specific definition of the ODOT operation. Unlike other operations, they require scalar multiplication after subtracting the ciphertext. And on the right side of the table, a mapping function is illustrated, which we will revisit later. After that, we define the cryptography accumulator, ACC, and initialize it. The input is a ciphertext, and the output is a tuple consisting of a zero-link polynomial and a polynomial whose coefficients are computed as b minus I, where b is the ciphertext applied to the function f. Here f is some mapping function, and notably, if u is the inner product of a and s, then the u's coefficient represent the encryption of f, where the input corresponds to the decryption of the ciphertext. And blind rotation is the process of multiplying the blind rotation key with ACC via homomorphic multiplication. Simply put, the blind rotation key is the encryption of monomial whose exponent is minus inner product A and S. After blind rotation, the constant term of ACC becomes F of decryption form of ciphertext. And the process of extracting this constant term is called LWE extraction. Now I'm going to describe the concept of the flexible scaling factor. First, let's take a look at how the AND gate operation works in this setting. The message is scaled by Q over 4, and the ODOT operation here is simply defined as addition. If we look at the truth table, we will see three cases. When both inputs are 0, the output is also 0. When the inputs are like this, and the output should be Q over 4. When both inputs are 1, the output is Q over 2. To help visualize this, imagine a circle where values increased by 1 in the clockwise direction. And we can place these output values in truth table accordingly like this. Next, we define a mapping function for these outputs. 0 and Q over 4 are both mapped to 0, and Q over 2 is mapped to 1. However, because of the negative property in the underlying structure, the mapping function f must satisfy the condition FV is equal to minus FV plus Q over 2. To meet this condition, we instead map the outputs to Q over 8 or minus Q over 8, and after extraction, we add Q over 8 to adjust the final result. As a result, 0 and Q over 4 are both mapped to 0, while Q over 2 is mapped to Q over 4, aligning correctly with the logic of the AND gate. Now let's look at the XOR gate and how it behaves differently from the AND gate. The ODOT operation in the XOR gate introduces additional noise compared to the AND gate. And this is because it includes a multiplication by 2 after performing a homomorphic subtraction. However, the noise margin for the XOR gate is actually larger than that of other gates. For most gates, the absolute value of noise must be smaller than Q/4 to ensure correct decryption. But for the XOR gate, it only needs to be smaller than Q/4. This relaxed requirements allows the XOR gate to tolerate more noise while still producing the correct output. And usually in many FHEW crypto systems, the scaling factor delta is set to Q/4. However, interestingly, if we set delta to Q/2, we can redefine the XOR gate's O-dot operation as a simple addition between ciphertext. And this change allows us to reduce the additional noise introduced during bootstrapping. As a result, it helps lower the probability of decryption failure that can occur due to noise flooding. This is one of the key benefits of using a flexible scaling factor. Next, we will explore how these benefits can be used to make bootstrapping more efficient. Recently, Chonera introduced in the CPD security for exact FHE schemes such as FHEW. And following this representation, many FHEW-like schemes must adjust their parameters to satisfy in the CPD security, ensuring that the failure probability is reduced to a negligible level. When applying our method in this context, we observe that the failure probability of the XOR gate is reduced beyond its necessity. While reducing failure probability is beneficial in some cases, in many real-world applications, reducing it more than required is unnecessary and may lead to inefficiency. To address this, we propose a new bootstrapping approach that utilizes the excessively reduced failure probability to make bootstrapping faster without compromising correctness or security. In the case of operating consecutive XOR gates, there is no need to bootstrap after each gate. We can simply convert this process to a series of additions. And this is because the failure probability is already reduced beyond necessary. And this figure illustrates that our proposed method is applied. We can bootstrap 5 consecutive XOR gate operations at once. However, this is not limited to just 5 gates. We can continue applying bootstrapping until the noise reaches a certain threshold, ensuring correctness while maximizing efficiency. We refer to this technique as overlap bootstrapping. To utilize overlap bootstrapping, the scaling factor must be set to Q/2. However, this approach is only compatible with certain gates. Gates like N and OR cannot define the mapping function f correctly when the scaling factor is Q/2. Fortunately, in many real-world applications, predicting the next operation is not challenging. This means that if we know the next gate operation in advance, we can adjust the scaling factor dynamically by generalizing the mapping function f in terms of the scaling factor. Notably, this approach does not require additional key generation or extra evaluations, making it both efficient and practical for real-world deployment. And let's look at how overlap bootstrapping works with this figure. We can just adjust the scaling factor to Q/2 when operating consecutive XOR gates. When an AND gate operation is the next step, we simply adjust scaling factor by bootstrapping right before executing the AND gate. Then if another sequence of consecutive XOR gate follows, we adjust the scaling factor back to Q/2. And while performing continuous additions, if the additional noise approaches a certain threshold, we can bootstrap once to reduce the noise efficiently, instead of bootstrapping after every gate. So this is SHA. In SHA3, there is a notion of a state which plays a central role in the hashing process. The SHA3 consists of two main phases, the absorbing phase and the squeezing phase. During the absorbing phase, the plain text blocks are XORed with the state. This process is conceptually similar to a sponge absorbing water, and after each XOR with the state, a F function is applied to further mix and hash the input. Once all plain text blocks are absorbed, the process moves to the squeezing phase, where the digest is generated from the internal state. F consists of 5 building blocks: zeta, rho, pi, g, and iota. Among these, only zeta and g, iota involve gate operations. Moreover, the XOR gate operation used in the iota step can be converted to the NOT gate operations, which are almost computation-free in FHEW-like systems. The zeta and g steps in SHA3 can be represented using these equations, and by applying our method, every XOR gate operations can be converted to a simple addition. And first, we start with the encrypted state using a scaling factor of QoR2. And in line 2, the scaling factor of the state value must be adjusted to QoR4, because in line 4, we need to perform AND gate operations on those values. And in line 3, we multiply the state by 2 to enable the XOR gated operation with the result of the AND gate. After completing the AND gate operation, the scaling factor should be adjusted back to QoR2. And finally, another bootstrapping in line 5 may be applied if the noise approaches a certain threshold. However, in this case, bootstrapping is not necessary since the failure probability remains small enough. And this demonstrates how our approach can flexibly and efficiently handle a sequence of mixed gate operation in the F function. Here are the results of our implementation. We achieved a runtime reduction of approximately 44%, and moreover, the maximum failure probability remains negligibly small compared to the benchmark. And we use only a single thread when we experiment this code. To conclude, our work introduces several key ideas to improve the efficiency of bootstrapping and FHEW schemes. First, by using a flexible scaling factor, we reduce the noise generated during XOR gate operations, making computation more stable. And second, we propose overlap bootstrapping, which liberates this reduced noise to make bootstrapping more efficient in cases involving consecutive XOR gates. Third, we show that if the next operation is known in advance, we can apply overlap bootstrapping even with mixed gate operations, not just XOR. This observation opens up possibilities for building a compiler that automatically optimizes homomorphic computations based on the operation sequence. And finally, we note that similar ideas have started to appear in other schemes like NTRU and CK case. And thank you for your attention.